we've been having trouble with delivery of the tutorials via the WebEx system. Apparently now WebEx requires you to sign up for a free account in order to view files. Everton and I are looking at a better way to do it by delivering the tutorial via the modal, just like we do the lectures. At the moment, we can easily convert to a Microsoft media file, which I think most people can handle. So we're going to try that and put it on the modal, and we'll send you a notice when we've got it loaded up. So what we want to do today is talk about the last lecture material we've covered. We've been looking at the processes that affect contaminants in the subsurface, specifically this week, retardation and reaction. So we've gone over the 4 processes that I think are important: advection, dispersion, retardation, and reaction. This is an interesting couple of little pictures. Retardation is represented by this bottom picture. So there's an empty bottle that you might do a distribution coefficient test in. You would put some aquifer solid, some groundwater, probably from your aquifer, spiked with various concentrations of the chemical of interest, and then you would equilibrate those by shaking. And it usually takes 24 to 72 hours to reach equilibrium. You would then analyze or centrifuge the sediment away and analyze the water. So that would determine how much of the chemical stayed in the water. You knew how much chemical you added by knowing the concentration in that original water. The difference then is how much mass went onto the solid. So that gives you your KD value. Reaction, well, this represents perhaps a mad scientist who's just found out that this new emerging organic contaminant, in fact, undergoes hydrolysis with some reaction, and he's fairly happy about that. This is another mad scientist, looks like a graduate student except for the white hair, who's testing to see if, in fact, he can get the reaction to occur by adding an oxidant or doing something else. For biodegradation, we have all this complex words that none of us really understand because we're not microbiologists. And this is a neat cartoon. I read it to be a graph that of something that's increasing and decreasing and concentrations going up and down. The supervisor and the graduate student. And the graduate student, of course, is eating an organic chemical. It looks like a substituted benzene. The question is, why is that graduate student eating that chemical? Well, it's sort of up here. When you eat chemicals, you get to reproduce, grow, and survive. That reminds us that the bacteria isn't eating those chemicals for our benefit. They're eating it for their benefit. And what we're often doing is tripping organisms to do something to our benefit that might not be their preferred approach. So let's get into the tutorial. So what I'm going to do is build on that initial tutorial that we had and get you to think about how you might do some remediation. So remember this problem we had. We had a plume that had 3 wells, and we were watching the change in concentration of contaminants. And the question is, what are we going to do? What we'd like to do is stop the chemicals from reaching well 3. It looks like nature's already done that for benzene, but the other 3 chemicals probably require some remediation. And even at this stage of our career, we can decide what might be appropriate. So, what's our objective? Well, I've set the objective as the water is clean or essentially free of those chemicals by well 3. So you can see down below that benzene's already 100% attenuated. So what remedial technology would you propose for benzene? Here's a list of possible technologies. You could pump the water out and treat it. You could sparge it, that is, add gas and allow the chemical to move from the aqueous phase to the vapor phase and leave the system. You could have some reaction carried out. You could do in situ biodegradation, in situ chemical oxidation, or the old standby monitor natural attenuation. Let nature do all the work. What do you think would be appropriate for benzene? What would be your favorite technology? Fortunately, I can't type any slower than I can sing, but it's not bad. So, what would you do for benzene? What would be your solution? So, we've got a suggestion from here of probably monitor natural attenuation. So, it appears to be working well enough. Why would we change? Yeah, I would say MNA. Okay, that was easy. It's doing not very much, just watching and monitoring. So for benzene, MNA. If MNA wasn't going to work, what might you do for benzene? For example, if we had set the requirement for benzene to be cleared up by row 2, well, we can look at the environmental properties. So for pump and treat, we probably require that the chemical be mobile and not highly sorbed. Well, we can look at the KOW, and that tells us about absorption. It looks like benzene is sorbed to some extent. It has a KOW, but it's still quite soluble. And so pump and treat would probably work. Maybe not perfectly, but it would work quite well. So pump and treat, I think, would be possible. What about volatilization or sparging? Well, remember, we're sparging a plume, not an apple. So it's Henry's law that we have to look at, the partitioning between the water and the vapor. And a rule of thumb that I found somewhere, and I honestly can't remember where, was that if Henry's law is greater than 0.01 millimeters of mercury, funny way to report it, it should be spargeable. Not necessarily easily, but you could at least entertain sparging. So benzene is twice, or an order, at least one order of magnitude above it. So benzene probably could be sparged. So we might pump and treat it, we might sparge it. What about a reaction? A biological reaction, in situ bio. Well, we go to our table of environment, which might support in situ bio, and you can see that aerobically, benzene does degrade, and anaerobically, it's not as certain, but there certainly are instances where it degrades. So if we were going to use that as a directive, we'd probably pick aerobic in situ biodegradation. We might combine that by sparging because we're adding air and air has oxygen. So in fact, we might be doing not sparging, but biosparging, where we get both biodegradation in situ and sparging. There are no natural chemical reactions that affect benzene, but certainly in situ bioremediation or in situ chemical oxidation, with certain oxidants can remove benzene. We're not going to emphasize that because Neil Thompson hasn't told us about in situ chemical oxidation yet. But it's my view that we probably could do that as well. So it looks like for benzene, we have the complete toolkit. All of those technologies probably can be applied. So for you, the problem is to figure out for that specific site, for that specific requirement, what is the best, what's the most cost-effective and reliable, et cetera, et cetera. Okay, benzene's easy. Let's move on to MTBE. And remember that MTBE seems to be undergoing some attenuation by well 3, but certainly with it too high a concentration. Same possibilities. So we've rejected MNA because we've already seen the effect. There is MTBE at well 3. What about pump and treat? Okay, KOW is really low. Solubility is huge. So that means it really likes to stay in the water and won't absorb. So probably pump and treat would be ideal. I'm getting some feedback from one of the mics. I have a feeling it's Everton. Your Portuguese, although everybody muted. That one? Well, if you're online, Diane, you might want to mute your computer so we don't hear anything. That mute you. So make sure you're on mute when you're attending. He's been there 15 times. People are registering as me. That's good. So back to MTBE. So it is really going to stay in water, so pump and treat would work. What about volatilization or sparging? Again, Henry's law. For MTBE, it's barely above our threshold. So that means it might work, but it'll be really slow. You'll have to push a lot of air through the system to make it work. Real people use MTBE sparging on occasion, but again, their view is that whereas benzene is spargeable, MTBE really requires a lot of gas to get much action. So probably we wouldn't want to try that. In situ bio, well, it looks like aerobic has a potential to degrade MTBE, but not a great one. And there's a number of papers that show us that there are systems that again, in situ chemical oxidation, we'd have to wait until Neil tells us, but if it's not commonly used. So for MTBE, the things aren't quite as easy. Pump and treat looks like a good one. Sparging is possible, but not desirable. Biological reactions don't look really strong. There's a maybe there. And we don't know about in situ chemical oxidation. Great, I think we got the microphones under control. I'm not getting any feedback. Thank you. 1,4-dioxane. Again, M&A didn't work. What about pump and treat? Well, dioxane is miscible. It's very, very soluble, doesn't absorb at all. So pump and treat would probably work. Is it volatile enough? Compared to this very high solubility, no. The Henry's law constant is very small. Note that it has the highest vapor pressure of any of the chemicals. So in its pure form, the pure naphtha is very volatile. But that's balanced by solubility. It's extremely soluble. And remember, Henry's law is sort of a balance between how volatile a chemical is versus how soluble. Looks like solubility wins, and dioxane is not strippable by sparging. So I apologize. We seem to have been kicked off a couple of times. Rather than keeping on with that, what we're going to do is just record the rest of the tutorial. We'll be active with the people here, and we'll try our best to relay their questions or comments to you. So we were talking about how to treat dioxane, and we identified pump and treat as probably the only technology that would likely work. What about TCE? Well, again, pump and treat. Well, of those chemicals, TCE is the most highly lowered. It's the least soluble and has the highest KOW. That's still not a huge number, and we could pump it and let desorption work, but it's not going to be as successful as it would be for the other chemicals.
So is there sort of a rule of thumb on the KOW, or is it so dependent on other things?
Yeah, it's hard. Is there a rule of thumb on that issue of KOW? Well, remember, it's really KD we're after, and it depends on the organic carbon content in the aquifer. So it's really KD that would be the director. And I think people develop a bit of a rule of thumb. So TCE, for example, with a KOW of 195, in a very clean aquifer would be reasonably pumpable. In an aquifer that had 0.1% organic matter, it wouldn't be terribly pumpable. Pump and treat has another problem, is that once the chemicals diffuse into low permeability zones, as there always are in systems, pump and treat requires diffusion back out, and that's a long process. So it inevitably becomes pump and pump and pump and pump and pump and pump and treat. You pump a lot longer than you think you have to. But it would certainly, pumping near well 3 would cut off the plume and eventually remove TCE from the groundwater. Sparging, well, it certainly has a Henry's law constant high enough. It should be the easiest of those chemicals to sparge, in fact. Reaction, in situ biological. Well, we look at TCE and we see, yes, under extremely anaerobic conditions, it degrades. So we could try and create those conditions by adding an electron donor like acetate or almost any organic matter, and turn the system extremely anaerobic. That has a disadvantage, of course, of making the aquifer very smelly and mobilizes metals. We'd also have to be worried about the breakdown products, cis-TCE and vinyl chloride, which aren't terribly degradable under that condition. So in situ bio would become quite complex. We might try initially to turn the system extremely anaerobic, but we then might have to turn the system aerobic to polish off the breakdown products. So that doesn't sound very desirable. In situ chemical oxidation does work, so that's a possibility as well. So, what did we come up with? Well, for benzene, I think MNA was the obvious. For MTBE, we thought that we could pump and treat, we could sparge it, we could add oxygen for bio. 1,4-dioxane was pump and treat, and we're not sure if ISCO worked. TCE is anaerobic bio or ISCO, both work, and pump and treat maybe as a third option. Well, remember, one of those technologies is benzene, and we're going to apply our technologies to a plume that contains all 4 chemicals. So if we do something like anaerobic bio, that's probably going to stop benzene degradation. So we have conflicting technologies here. So, what technology do you think we should apply? or what series of technologies if you want to get more expensive and more complex?
So there's biospar very close to the soil, or close to the front, depending on how clean it is, and see what's really getting by that. Kind of got everything else.
Okay, the idea was to do a sequential treatment, and that would probably be a biosparging near the front. So we would get, certainly benzene would keep degrading, we think. MTBE would be sparged. Dioxane, nothing would happen to dioxane. TCE, nothing would happen to TCE. So we'd have a dioxane TCE plume. What would we then do? Yeah, pump whatever gets through. Remember, I said for TCE it would probably work. So let's try that. So that would be okay. Any other strategy? Is there a simpler strategy? Is there one technology that you might try?
Only pump and treat?
Yeah, it looks like the only pump and treat is mentioned, and it looks like it would be limited by how fast it can get rid of PCD. So that maybe isn't a bad overall strategy. Pump and treat. Might have to do a lot of pumping, but never mind. So there's an example of how, in a very simplistic way, you can very quickly sort through the chemical issues and get a very quick handle on what might work and what certainly won't work. That's just using the environmental property.
So is it, like you mentioned, if you do something to reduce the concentrations before pump and treat, does that greatly affect the cost of the pump and treat, or is it not worth it to do a first step to reduce concentration?
So would reducing concentrations help? Well, not really, because pump and treat pumps water. So it's the volume of water that costs. There might be a treatment cost as well, so maybe there is a benefit. But in terms of the volume of water, it probably doesn't make a big difference. You're going to focus your treatment on the high concentration. It'd be wasteful to spend a lot of effort on very low concentrations, which might be the ones to get rid of for pump and treat. For instance, if you had a core of the plume that you're going to target pump and treat for, and low concentrations elsewhere, getting rid of the low concentrations might save you a lot of water to the pump. Pretty hard to focus in that sort of organized way. So that's one of the reasons you don't see sequential treatment systems. It's expensive. It's hard to get them lined up perfectly. Anything else? Okay, that's an interesting exercise, I guess. Okay, just a reminder from the lectures we had. We were talking about this plume that Hubbert created, where we had BTX dissolved in water moving through the Borden aquifer. And we asked the question, why was the mass loss rate slower in the field than in the lab? Remember, in the field, we looked at the rate of mass loss through extensive monitoring, and in the field, we created optimal conditions, and we watched the biodegradation. We did the lab studies to confirm that aerobic biodegradation was possible, not really to derive rates or anything like that. The field, it took more than 500 days to get benzene going down. In the lab, it took less than 150 days. The lab is much faster. And we asked the question, why? Remember what we suggested was the main control of those differences?
Anoxy.
Yeah, the anoxy of the plume travels along, the BTX uses the oxygen before the BTX is removed, and we're left with an anaerobic plume. In the lab, we added oxygen and kept things equilibrated and shaken, so oxygen was always available. So what supplies oxygen to the BPX plume in the field? Dispersion, maybe a bit of advection. Dispersion is a slow process. So we're sort of stuck in the field situation with a slow process, usually being the rate controlling step. So the experience from Borden said that things like MTBE, methanol were degradable. BPX and methanol were degradable. MTBE was apparently recalcitrant. That was the observation from Tina's Hubbard's work. Dispersion mixing was the key rate controlling step. It wasn't some microbial factor. So to optimize the system for in situ bio, the need really is, first of all, to optimize the electron acceptor. So adding bacteria, adding nutrients really isn't going to optimize it. Getting oxygen into the system is the first priority for optimization. After you do that, there might be subsequent secondary optimization. But getting electron acceptors in there looks like the first. And to emphasize that, Mario Schirmer did some modeling, and he modeled with various rates of biodegradation to see what he could do to match what you see in the plume. That is 500-day persistent, but things going down. And it turned out that he used Borden parameters for advection and dispersion, and that worked well with any biodegradation rate he could find in the literature. So whether it was relatively fast or relatively slow, it didn't change the field situation. And that really emphasizes that the rate of biodegradation, the microbial rate of biodegradation, would not be rate controlling step. It was this dispersion. Well, Mario did something else as well. He proposed that we should go out and look for the plume 9 years after we put it in the ground. Actually, the American Petroleum Institute asked us if we could do that. And I facetiously said, that's a needle in the haystack. How can you find a plume that's a couple of 100 kilometers or a couple of 100 meters away 9 years after? And these are very small targets. They said, well, I think it's worth the effort. At that time, MTBE was a big issue. So Mario Schirmer, a PhD student at the time, said, well, I think I can find the plume. It's Borden. It should be quite predictable. Groundwater flow direction seems constant. So we ran a simplistic model. MTBE was conservative, so it was an advection dispersion model. And said, well, now the MTBE plume should be out there. So API paid for monitoring to go in, and surprisingly, to me anyway, we found the plume. We ended up with wells that had no MTBE in it on the outside of where he found the MTBE, suggesting that, in fact, he had found the plume. He had zeros around the outside, and the plume was essentially where he thought it would be. So, during Tina's work, the work we've already shown, the data is scattered. And it turns out that that data is too scattered to say that that trend is anything other than a flat line. You see, with Mario's lines added, you now can see that maybe that scatter has some consistency. Statistically, it didn't, but what Mario did was add that point down there. So a simplistic view would be a 2-point persistence curve from what we had at the start to what Mario found at the end. And even if he's out by 100%, that number only goes like this. So even for a lot of uncertainty in the field, and there certainly was, when you look in that paper, the reviewers had many good criticisms, a few of which we couldn't completely dismiss, but had to acknowledge. So that number could be quite variable, but it's still really small. So you go back and look at this data and put the best fit line through the data, and that dotted line is the best fit line, I think. But it's not statistically reliable. At that point, now maybe the rate becomes somewhere in between those two. So it looks like MTBE eventually did disappear. Or almost disappear. So, and many people since then have shown that MTBE can be degraded anaerobically under, again, extremely anaerobic conditions. So it looks like MTBE is not persistent all the time, everywhere. On the other hand, when you look at the reason MTBE was banned in the U.S., it was because it was persistent in groundwater. The real-world experience was that it was showing up in drinking water wells tens or kilometers away from where it probably went in. So, to get the degradation we need to get rid of that chemical requires a lot more than what normally occurs at field sites. Remember, MTBE is very soluble, so it's often at the source present in milligram per liter quantity, and people were trying to get it down to 10 micrograms per liter, many orders of magnitude reduction in concentration. So that would require a very good biological process as well as dispersion to do it. So in the real world, the default assumption was that it was persistent and mobile. But the literature has examples where it wasn't persistent, apparently, but was still mobile. That brings up an issue with the literature. Literature prizes unique contributions. So it's easy to publish the first paper on something new, like MTBE degrading in the field. That's why that paper was published. One of the first sort of reasonably well-documented field cases where it really does look like it's degraded. And there was lab support as well that said, yes, aerobically it could degrade. Well, if 50 other people found in their site it was degrading, it would be hard to publish those papers because the editor would say, well, what's new? We only publish new ideas. Well, the literature is not a statistically significant survey of what happens in the real world. It really gives you possibilities. It doesn't tell you whether or not that possibility is recognized often or infrequently. It just says that's possible. So don't interpret too much from the literature in terms of what might occur at a site. Okay, we want to just do a little plume as well. This is a coal tar creosote plume that was emplaced at Borden, of course. And there are 3 papers that describe parts of it. The first 2 papers by Mark King really describe the bulk of what I'm going to say. Michelle Fraser came along later and resampled the plume now after 14 years. So it's a fairly long monitoring time for a research plume. Normally, research plumes are modified for 4 years. That's the lifetime of a PhD student. That was Mark King's lifetime. So here's what we did. We emplaced coal tar creosote. That's a waste product that's used to preserve wood, coal gasification, and various industrial sources produce coal tar, all the same sort of chemistry. So what we did was created a source of coal tar creosote in the Borden aquifer. We emplaced 74 kilograms of coal tar creosote liquid. We put it in and mixed it with a coarse sand at less than residual saturation so that it wasn't really mobile, we hope. And the coarse sand was to keep the permeability of the sand about equivalent to the Borden sand permeability. That is, we didn't want to reduce the permeability by adding creosote to the pore space, so we used the coarser, more permeable sand. And we didn't want to deal with issues like volatilization, so we emplaced it well below the water table. So there's no volatilization loss. This is a picture of how we emplaced it. You can see the safety precautions in 1991 were embarrassing. This is the drum of coal tar creosote. Measured amounts are mixed with weighed amounts of sand to get a fairly consistent mixture, and that sand is trimming into a hole. To emplace the source, first of all, we drove in this sheet piling box. So it's about 6 meters by 2 meters. We then dewatered the sand in the box with 2 wells at each end. Then we excavated the sand with a backhoe. We then emplaced the coal tar creosote in the bottom of the hole. We actually emplaced it as 2 blocks with board and sand around it by trimming it in under well-controlled conditions. This person's now a principal in a major consulting company. I presume he's still giving donations to the university because this picture hasn't gone out on the web at all. Because he's going under the ground surface, and coal tar creosote isn't the most pleasant smelling stuff. He's got a respirator system, but we did take some precaution and protection. So after we got it in place, we backfilled with board and sand and then took the sheet piling out of the ground. So that allowed the groundwater flow, which was essentially horizontal, to resume. It goes through the source, dissolves the source, and creates plumes. And our interest was, what do those plumes look like? So here are some of the chemicals that were in place. Again, there's some hydrocarbons, aromatic, xylene, phenol, and substituted phenols, PAHs, and NSO compounds like carbazole and dibenzofuran. You note that one of these chemicals is naphthalene. And you notice the solubility of pure naphthalene is 32 milligrams per liter. So think back to your tutorial where you're asked what was the concentration of naphthalene near a source. And everybody, or a number of people, took that solubility, applied Raoult's law, and came up with a number. And surprising to them, they found their number was wrong. Why was it wrong? And it was wrong. Okay. Exactly. The comment here is that that number, 32, is not the liquid solubility, it's the solubility of a solid. We go back to our lectures, we noted that naphthalene is one of the few chemicals we'll deal with that in fact is a solid at 25 degrees C and 1 atmosphere pressure. So its solubility is the solubility of solid naphthalene. In a naphthalene, it exists as a liquid, not a solid. And the liquid naphthalene is much more soluble than solid naphthalene. That's 150. That's the correct answer of what, 15, I think, was the mole fraction of 0.1. So just a reminder that that enters into it. That was actually a big issue. We had talked to a coal tar creosote company, and they were very surprised at the high naphthalene concentrations in their plume. They were really worried because it was above what they would predict with Raoult's law, well above. And Mark King pointed out to them that they were using the wrong solubility value in Raoult's law, and that simplified their life immensely. Yes?
So we have all those melting points along the side there,
Yeah.
and a lot of them are above 5 degrees Celsius.
Yeah.
So wouldn't those also reduce that as solid?
Yeah, they could be. And you'd have to look back at how they determine the solubility. In many cases, people do solubility at a slightly higher temperature and extrapolate back with thermodynamic constants to get a liquid solubility. But no, that would be a good point. Why wouldn't you, for carbazole, for instance, what is its real solubility? Is it the solid solubility? Do we have to correct for it? Good point. Okay, so we weren't really considering remediation, but let's make up a remedial objective. Certainly, a real objective during the experiment was to preserve the groundwater down gradient from being contaminated. My colleagues wanted to use that groundwater for their experiment. We didn't want to have to clean it up. Well, as long as they couldn't detect any of those chemicals 80 or 100 meters down gradient, that was okay. What we'd like is the long-term plume not to be more than 60 meters. We could afford to give up 60 meters of aquifer, but no more. And just to show good faith, we wanted to remove a significant amount of mobile organisms. We wanted to show that we weren't just doing nothing, but in fact we were monitoring nature, which was doing quite well. So, short plumes and mass being removed are our objectives. Let's see if natural attenuation was doing that. So here's a monitoring network. The sources are the green boxes at the bottom. The dots are multi-level wells going down gradient. So this is a plan view. And these are the wells that were sampled on the different sampling dates that we'll show. Each of those wells, in fact, has 14 points spread vertically at about 15 centimeter spacing. So near the source, we have wells spaced typically a half a meter or less apart with vertical sampling every 15 centimeters. So it's not hard to end up with 800 samples to monitor a plume. Or the best one we had was 2,800 samples. That's a lot of samples. This isn't the real world. Well, what did we expect in terms of the dissolution of the source? This is a funny way to express it, but it's the mass discharge relative to the initial mass discharge. So how would the mass discharge evolve over time? This is replicates the shape of the curves if you were just considering concentration. But we were really looking for the mass discharge. That is, how much mass is coming through some cross-sectional area, some water flux, and with a certain concentration. So on a fence of wells, typically near the source, somewhere down in here, we would sample all of the wells, and for each one we would calculate the mass flux for that particular part of the aquifer, and then add them all up. And this is what you would expect if Réault's law applies. It's an interesting curve. Our general expectation is that over time, as the chemical dissolves, its concentration becomes less and less. Mass is being put into the water. So for chemicals like phenol, which are very soluble, it should leave the source very quickly. Naphthalene is the least soluble of these lower ones, and so it will leave last. The surprise for many of us was, in fact, that the concentrations of some chemicals, or the mass discharge of some chemicals, goes up over time. And nobody expects that. That's counterintuitive. We saw that in sparging experiments in the lab. The concentrations of some chemicals goes up over time as we remove mass. It's not that the mass is increasing in the source. The mass is decreasing. But the flux coming out, or the concentration near the source, is going up. Why? Well, because of Réault's law. Réault's law says the concentration in the water is equal to the mole fraction in the source times solubility. This tells us that the mole fraction of these less soluble chemicals is going up. And when you think about it, that's exactly what should happen. The more soluble chemicals are being removed preferentially, so their mass fraction is going down precipitously. So the other mole fractions have to go up. So for many of the chemicals of interest to us, things like phenanthrene or anthracene goes up, and eventually it'll come down. For methylnaphthalene, it should be coming down in the time period of our experiment. For 9 years or 14 years, we're somewhere out here. So that's interesting. The source should be doing weird things. Well, what are the evidences of attenuation in that plume? Remember, we don't want long plumes. Well, if we look at the extent of the plume, that is, over time, and we've got all these snapshots over 14 years, the actual is how far the plume was observed, how far it was detected. This is how far the plume could have gone by advection and retardation. So we just applied the retardation equation using a KD that we calculated, using the correlations, FOC we measured, correlations with KOW to get KOC. That calculates KD, plug it into the retardation equation, and we get a retardation factor. That is the velocity of the groundwater relative to the velocity of the contaminant. And this is for that period of time, 14 years, how far the plume should be. So it's clear the plumes aren't as far as they should be. So we can't account for where the plume is by advection, dispersion, retardation. That points us towards some reaction has occurred. So our hypothesis is there's a reaction going on. As you might expect, different chemicals are behaving differently. So looking at the evolution of plume, we're looking here at the different days, and this is really a snapshot of where the plume is, or a group of chemicals. So we sensed there were three different patterns here. Plumes that grew and shrank. So here's naphthalene. So it was this far. It grew by that day. Looks like it's shrinking. It's shrunk. That's funny, isn't it? So a plume, instead of evolving by extending over time, continuously, grows and then shrinks. That needs explanation, doesn't it? Grow, then, we're not sure. Well, let's look at dibenzofurans. Well, it started there, about the same. It grew a little bit by then, about the same, about the same, about the same. So is it growing or shrinking, steady? Don't know. Looks like it's steady. Plumes that are still growing, acetylnaphthalene. This one. So it was there, grew a little bit, grew more. Looks like it might still be growing. So what plumes are you worried about? Remember, we don't want contamination 50 meters down gradient. This scale is, I think, 50 meters is the end of the wall. So all of these plumes are currently within the boundary for our remedial objective. Which plumes are you worried about? Yeah, the ones that are still growing. Now, there's no guarantee that ones that have apparently gone steady won't grow again. Who knows? But certainly the plumes that are growing still are ones of concern. And that would be the general response, I think, by the public. If the plume's growing, people are worried. You can sometimes get away with putting a very good monitoring well in front and say, well, if the plume gets to there, I'll do something. And if you can clearly define what you plan to do, and it's clear you're able to do that, they might accept it. They don't want you using their drinking water well as the monitoring well. But if the plumes are shrinking or steady, people are more likely to buy into the idea of natural attenuation. Well, let's look at some of the plumes. Here's the M plus P xylene plume. These are the different days that we have samples. You can see the plume was moving along quite well, moving at almost the groundwater velocity. It was for its front anyway. It was growing, shrinking, shrinking, essentially gone. Let's look at even a more interesting case, phenol. So it started to grow, grew, and again was gone quickly. By day 600, just 1 or 2 sampling points had it, and a few here. So phenol is the most mobile chemical, but it appears to disappear very quickly. So how much mass is in those plumes? So in each day, by taking all the samples and adding them up, you can calculate how much mass is present. You can actually estimate the absorbed mass from the dissolved mass and add that in as well. And that's what Mark did. So we claim this represents the dissolved and absorbed mass in the plume. So that's mass that got beyond 2.7 meters from the source. That's the arbitrary definition of the plume. And here's the mass over time from those sampling snapshots. You see, interestingly, the naphthalene mass goes up, and then it's gone down. Well, the mass in the plume has in fact gone down. At the same time, the plume grew, and then it shrunk in cohort with that mass. So we look at 1-methylnaphthalene, phenanthroline, that plume was growing, and the amount of mass in the plume is still growing. Maybe that's why the plume is growing. The mass keeps coming in, keeps moving along. 1-methylnaphthalene grew and then started to shrink in the last 2 samplings, and that's maybe consistent with the mass, the mass in the plume has gone down. So it looks like getting rid of mass from the plume also is important in documenting attenuation. So the naphthalene plume, is it declining because the mass leaching from the source is declining? Or is it because it's reactive? That's really the 2 major ways to affect how much mass is in the plume. Either have less coming in from the source, or remove more from the plume itself. Would we expect mass from the source to be going down? Let's go back. Well, naphthalene is down here. Yes, Rayle's law says that we should expect a continuous decline in the mass flux coming out of the source, the mass discharge. Yes, but that can contribute. So if you're right, the comment was, well, still wouldn't the mass be increasing? Yes, the cumulative mass in the plume, if this was the only process, would be going up. But in terms of mass removal process, if a mass removal process can remove a certain mass discharge, and you now drop below that input, then you should see the plume mass go down. That would be the rationality. So for many of the chemicals that are shrinking, the mass leaching from the source could be declining, and it may not require the mass loss rate in the plume to go up, but it does require mass loss in the plume. Well, Mark did some microcosm experiments and determined that aerobically all those chemicals were degradable. So that allows us to bring in aerobic degradation. And again, we know something about oxygen consumption and availability. It's a diffusion, dispersion controlled process. There's been a number of attempts to model the plumes. It's turned out to be very difficult to pick out individual plumes and model them. So that's not been terribly successful. Well, how much mass is lost? Well, let's talk about what happens in the source area. That's up to about 2.7 meters from the source. We call that the source area. So here were some mass balances that Mark set up. So the mass flux into the plume over a certain time period was the time period times the groundwater discharge through a cross-sectional area. So what you would do would be to look at the concentration along that fence at one time, look at the concentration along the fence at the next time, and integrate that over that time interval. So that would say how much mass has come in over the two sampling periods.
What application into that?
Into the flux. I think we screwed up the thing in there. So that would be the flux of groundwater, and we need the concentration. So that would be, we don't actually have concentration anywhere, do we? Yeah. Yeah, it should be a mass, it shouldn't be just groundwater discharge, it should be the mass discharge at each of the two times. Or an average mass discharge over the time interval. I think that was it. You would take the time before and the time after, average them, and say that was the mass discharge of the chemical over that time period, delta T. And it has a cross-sectional area that the plume's going in. So the mass in the plume was simply the mass that's dissolved from monitoring data, and the mass sorbed, which just was from applying the Kb equation to the average dissolved contaminant concentration. That sort of works, but it's crude. So the mass transformed in the plume is equal to the mass that comes in minus the change in the mass in the plume. So over a time period, if you said X comes in and there's only Y in the plume, then how much is degraded is X minus Y. And he estimated what was coming into the plume by applying Raoult's law to the source. Or sorry, what was leaching out of the Napa was calculated by Raoult's law. What was surviving until it got in the plume was again done by the monitoring here and the changing concentrations over time. So let's go through it here. So for M-xylene, the monitoring documented that amount of mass in the plume. Monitoring at the fence over the time interval from the previous, said that much is entering the plume. How much did we find in the plume? None. Oh, sorry. Dissolved is how much dissolved from the source, Raoult's law. How much entered the plume was the monitoring fence. How much was in the plume was the monitoring in the plume. So the mass that's lost from the source is how much dissolved minus how much got into the plume. So that's about 18%. The difference is about 20%. Once it got in the plume, then the difference between what's in the plume and what entered the plume is mass loss in the plume. So if we then compare what's in the plume to what probably dissolved, we get how much was degraded. So up till each sampling point, the amount that was degraded is a very impressive number. This much dissolved, and if this much made it into the plume, but the plume only has this much, that's a big difference in each case. So this mass loss process is really accounting for the bulk of what we're not seeing in the plume. It's not that the source has died off completely, at least in early days. But for most of these chemicals, it's that the removal in the plume has been very impressive. Notice that these chemicals where we find significant mass loss in the source are less soluble. The more soluble chemical seems to lose their mass in the fluid. And for hydrogeologists, that's really good, because these are the mobile chemicals. It turns out their mass is being removed most successfully. There's a number of reasons why that might be the case. None of them are so clear that we would declare them here. Well, that's pretty impressive mass loss in the fluid. So it looks like we can look towards biotransformation as an important process. For many chemicals, the source is depleted already. So after 14 or so years, we've got biodegradation ongoing. It's been successful in the plume. The source is depleted in phenols and aromatic hydrocarbons. We just have some PAHs and MSOs left. That's a real concern. So, are we meeting our objective? Let's go back to our objective. So I'm trying to preserve a coal tar creosote-free groundwater 80 meters down gradient. I think we can say yes. None of those plumes made it to the end of our 50-meter or 60-meter monitoring box. So I think that's a winner. Are we confident we're going to restrict the dissolved plume lengths to 60 meters forever? For most of those plumes, they're either shrinking or stable, but a few are still growing. Well, if you were skeptical, as you should be, I think you'd be saying, no, I'm not yet confident. You'd probably ask me to continue to monitor. Have we removed significant mass of these mobile chemicals? Well, that previous slide says yes. We've really removed almost all of the chemicals that got in the plume. But we're still not really comfortable about that 60 meters forever. So I think that's, for us, it was a good learning. We didn't expect to see these sorts of mass declines. And if you go back to some real plumes, there's been a few that have been monitored extensively. And the same thing is evident. The plumes aren't increasing concentrations in the plume or the distribution of the plume to the extent you would expect, given what's still in the source. So it really looks like the major attenuation of some of these real-world plumes. There's also degradation in the source. Or sorry, degradation in the plume. So I think that's now my expectation, that at real coal tar creosote or petroleum hydrocarbon contaminated site, the plume should be shorter than I would calculate, and there should be less mass in that plume than I would estimate by Reynolds law for the approaches. Doesn't mean it always occurs, it's just now my default. Okay, just to finish that off, what did we do? Well, we actually took active remedial action, which is very unusual for us. So in December, about a year ago, 2 years ago, sorry, we dug up the source. We did what's called a dig and dump. That's the most common remedial technology, I think, at gasoline service stations, because generally the contamination is shallow. It's normally around the tanks or tubing that's leaked, and they have to be dug up anyway. So normally the waste material can be dug up. The concentrations that are acceptable by most normal landfills, municipal landfills, are such that you can usually dispose of that anywhere. It's not considered hazardous material. So in December, we dug up the source. How did we do that? Well, we installed sheet piling, because we knew where the source was. We then partially dewatered the source, and then just dug it out with a backhoe. Laid it on some plastic while we tested it to see what landfill it could go to. We actually managed to find that all the chemicals were below detection. And that, of course, is improved by allowing us to stay out for a while, mixing clean sand with dirty sand, all sorts of techniques you could try. We didn't try any of those. We had taken a core through that material initially and tested it, and again found that the average concentration was low. Clearly there was a zone of high concentration, but diluted with the rest of the sand, it was acceptable for a normal weight. In fact, the base took that sand and used it for construction purposes. So we dug out that sand, then we backfilled with clean sand that the base provided us, then removed the sheet piling, and we've now forgotten about that source. It no longer is there.
Yeah, cores with the concentration what we expected in the last fall.
With the concentration what we expected, we didn't actually do enough coring to do that. What we did was just took a total core of the sand, which includes mostly clean sand at the top and a small zone of contaminated sand. We took a subset of all of that, homogenized it, and submitted it. That's what the legislation requires you to do, to get an average of all the sand you're going to supply. Mark King actually did coring of that source, I think within a year of placing it. And the numbers he got were so variable that you couldn't actually reliably determine how much was there. It was sort of 100 kilograms plus or minus 75 kilograms, the uncertainty in the source. So that's from taking a core and then subsampling it. So you end up with 100 little subsamples, but the scatter is from 0 to 10% coal tar creosote, and it's so scattered, the average has very little significance. And that's surprising because we mixed the coal tar creosote with a uniform sand. We emplaced it as uniform sand. And the coal tar moved around enough to get very inhomogeneous in uniform sand. So when other people have suggested for some of our other sources that we core it, we go back to this experience and say, well, I'm probably going to need 1,000 sampling points to derive a reasonable average. We'll have the money or the effort to do that. So I think coring in real sources is unreliable in terms of getting a mass that's there. There's other reasons to core, but to get a mass balance is, I think, is not on. We now won't core to get mass balance. Our experience has just been so negative. All that effort for a very uncertain number doesn't do us any good. So we've dug out the source, but what about the plume? We haven't done anything to the plume. Still there. So the life of the plume should be shorter now. We don't have an ongoing dissolving source, so that should be good. The time frame should be shorter. We think the plume will degrade faster because we're no longer have this huge DO sink up gradient of the source. So oxygen should start moving through that area, and that should improve the accessibility of the dissolved chemicals to oxygen. So we expect the plume to disappear on its own without growing too much more. And we have one well that's just downgraded in front of the plume that we continue to monitor. Might be quite interesting if we had the money and the interest to continue to sample that plume. Practical problem was, in doing all of this earthworks, we actually destroyed almost all of the piezometers near the source. So So it would be very difficult to continue to do mass balances of the plume as it declines. We're just looking to see if it does or does not advance any further. So we're confident that we'll monitor this down gradient and nothing will show up. If something shows up, our commitment to the base is to do something about it. And in a few weeks, we'll talk about funnel and gates and permeable reactive barriers. It turns out we actually have a funnel and gate just down gradient of this plume that we could implement if we had to stop the plume from going any further. But that'll be mentioned in the permeable reactive barrier lecture in about 3 weeks. So we don't know that we're going to meet the long-term goal of the plume not moving any further. So we continue to monitor that one. So we're confident that we'll monitor this down gradient. Nothing will show up. If something shows up, our commitment is to do something about it. And in a few weeks, we'll talk about funnel and gate and permeable reactive barrier. It turns out we actually have a funnel and gate just down gradient of this plume that we could implement if we had to stop. So, for monitoring natural attenuation, advection is bad. It's moving the contaminant to where we don't want it. Dispersion, absorption, and reaction then are the processes that we're relying on. Dispersion's weak. Absorption temporarily holds up contaminants and probably spreads contaminants over a larger volume of water. So if concentration is our objective, absorption may be very helpful. But if mass flux or something like that is our objective, it might not be useful. So these may be sufficient in some cases, but most of the time with organics, we're after 3 to 6 orders of magnitude reduction in concentration. It's hard to get that by reasonable dispersion. So for mobile organics, we think there has to be some naturally occurring reaction for M&A to be usually successful. And I think that's why M&A for hydrocarbons is the default solution. For solvents, because the biodegradation processes aren't apparently as active, especially in aerobic systems, I think there'll be more chlorinated solvent plumes that require remediation as opposed to letting nature look after it. That's been the experience so far. And we have to be careful that we provide enough information and enough evidence of M&A that it meets our objective. And the objective really is risk management, I think. And so if we have a big risk, that is, if the impact of being wrong is high, then we probably need a higher level of understanding of these processes. If there's no receptor, quite common, or no nearby receptor, it's quite common for M&A to be applied more loosely without as much supporting data. And in some cases, biodegradation can be really impressive. It can remove a lot of mass over a lot of time. So what we've done is talked about the processes of advection, dispersion, retardation, reaction, the processes that control the migration of contaminants in the subsurface, especially for organics. And we've done it within the M&A sort of framework to indicate that in some cases, natural processes can bring about good remediation. Many people would argue, I think with some justification, that truly letting polluters off the hook. They polluted, they should pay. Polluter pay principle. Some cases, when you look at what the remediation's done, it's spent a lot of money and actually not accomplished much more than what natural attenuation would have done. So you have to balance those points of view that I call it, most hydrogeologists are good housekeepers. If something's dirty, they want to clean it up. That's just the first reaction. Some cases, you might in fact find that you can't do any better than nature. In other cases, you might find that nature does okay. You could do better, but is it worth doing better in that case? And in other cases, you're going to say nature can't do it. I've really got to do the remediation myself, and that's why we're going to discuss remedial technology dominantly in the rest of the course, just to show you what's available, what ideas you can apply. So, comments, questions? So next week, Everton's giving the lectures. They should be posted by Monday. He's doing a tutorial from Brazil, so there's no need for us to meet. It'll be on your computer. Okay, thanks very much.